which I don't have, actually I don't have it installed on this machine. This is my school machine, so I can't put my Steam account and everything, all my, I don't know how many games I've gotten off Steam at this point, but way too many. The interesting thing I find about this game is it's a kind of an RPG, JRPG style game. Its graphics are this really interesting combination of kind of pixel art and 3D. It actually is built with the Unreal Engine. I was kind of surprised by that. It's not your typical Unreal game, certainly. Unreal Engine games, you tend to see them and be like, oh, first-person shooter, third-person shooter type games. But this one is obviously not that style, much more a classic JRPG, certainly generations beyond our good old Pokemon, but it's got that similar battle fight, kind of when you get down to your enemies and so on. But anyway, the interesting thing I find out about it is the feeling that it produces, that it really gives this feeling of looking at something in miniature. It feels like you're looking at a model, that you are, playing with sort of a tabletop toy. And maybe it's accentuated to me in that doing some stop motion animation, working with some Lego animation and having a Lego city sort of thing. There's certain phenomena that they mimic in this game that are very much akin to if you tried photographing something to make it, not necessarily make it look miniature, but the effect is that it winds up looking miniature, and you can kind of fake this effect in real photography to make things look miniature, like cities and kind of landscape photography and stuff. And in this one, it's also there. And it's this kind of really strong depth of field effect, right? Depth of field is really saying, well, where is the focus? What's the plane of focus of the camera here? All right, so obviously the focus is on our character here in the center, our protagonist, our hero. And things that are close to the camera are blurred. Things that are far from the camera are also blurred. They're a little bit uneven in their blurriness here, but that's okay. That kind of, it still lends to the effect. But this severe depth of field, meaning the focus plane of the lens, is right here, and front and back is very blurry. That's the depth of field. How much? Now, if it had infinite depth of field, it was a very small camera lens, like a lot of our lenses that we get used to on our cell phone cameras, right, or iPhones. You typically wind up with very deep depth of field in your photography. You don't often see that sort of blurry, smeary background effect unless you ask for it. For portraits and things, there's always like a filter you can apply or a model that the camera can build during capture that'll give it more a sense of actually capturing depth information, so later on you can kind of add these effects and so on. So it's interesting now that what started off as a lens phenomena, I hate to call it an artifact, artifacts sound bad sometimes, has become this real technique to give you a sense of physical presence with regards to something like this, or even with regards to a portrait, or how close are you to the image and so on. How warm does it feel, how comfortable, how dreamlike is it, and so on, achieved by this real effect of saying, okay, where is your focus and what's going on, what is the lens like, and so on. So I really like this background, and I find it a good example of kind of mimicking a lens effect that gives you a certain mood, kind of a really fun one. So that's bigger. Kick things off today with kind of a little bit of a fun background. So I should always like to keep notes right in here. So here's a key term: tilt shift and depth of field. I'm going to put that in lens effects. So that might be achieved by some sort of post-processing and breaking the scene down into different parts to say, okay, I've got to render the background, then the midground, then the foreground You know, how do I do it? Do I try to blur every object? Do I check everything? And it's difficult to actually do a blur effect in a fragment shader when you're still modeling everything, right? We really can't do that. We have to wait for that as a sort of post-processing effect. So usually these sort of things will be done as some sort of multi-pass rendering that we've been talking about, or multi-target, well, maybe a multi-target rendering sort of thing. It'd be interesting to say, well, okay, you know, how can you take advantage of that? So with those sorts of things in mind. Now another technique, we talked a lot about these kind of multi-target, multi-pass. We talk about those a little bit more every so often, techniques that wind up being generated by what we can do with these mechanics. In a game, or in any interactive application, you might find it necessary to pick an object, to click on something, to point at something, to kind of figure out where something that the user is interested in is at. So your first inclination, I mean, before I show this, let's see, it's not anyone who's online or, you know, or here in person, shout it out. What would be your first inclination to figure out where something is in the scene that you're clicking on? Right? I actually heard somebody say, who's here in person, I won't let him know, suggest something in the Unity to figure out how you're clicking an object. And so anyone have any ideas? That person? Ray casting, right? Where you shoot a ray and you say, all right, I shoot a ray from the point of view of the viewer through a certain pixel, and hopefully it hits an object. If it hits that object, great. Now, one of the problems with that is figuring out, well, okay, how do we figure out if that ray hits an object? Right? If we had to do collision detection on a model, that gets really complicated, right? Models are made of all kinds of polygons and so on. Do you render, you know, how do you figure out where a ray hits some representation of a model, right? And it turns out that in a lot of raster-based or in a lot of, you know, engines that we're not using, you know, ray tracing or path tracing or things like that, where we have this capability, one of the big techniques that's used is really kind of, feels like a hack to me, but I guess it is. It kind of qualifies as a hack, where it'll do things like draw the scene into an off-screen buffer and color interesting objects that are selectable, color them distinct colors. So you wind up with a buffer or a frame buffer that never gets shown to the player, the user, and it only has to get done instantaneously because it's just a click. So there's not, you know, it's not like you're doing this over and over again. Really, it's just that moment of click. You need to render out this somewhere, make some decisions. So you really just need to figure out, okay, where am I clicking with regards to my frame buffer that's going to be on the scene? And what color is it? And that's the object. So it winds up being a relatively simple lookup. Right? So you actually avoid the whole ray cast, hitting an object, and so on. It's just really just saying, okay, where's this pixel on the screen? What color is it? Then you can kind of look up based on that. Sounds pretty hacky, but, you know, in a nutshell, this is how it's often worked. To grab their own here. The trick behind 3D picking is very simple. Running index to each triangle, have the fragment shader output the index of the triangle that the pixel belongs to, right? So it's an index or color, right? End result, we get a color buffer that doesn't contain colors, perhaps, or you could view them and see what they look like, but they're really not to be used as colors. They're used as an index to figure out what triangle or what model it belongs to, right? So this is yet another really useful application of our sort of off-screen rendering, off-screen buffer, isn't it? So that's a fun one. Make a little note of that in here as well. Get back here. I wish I could just write on a whiteboard, but and I'll even, in this case, we'll put this link there. All right. So where's the common theme? I'm kind of rambling around here a little bit, in terms of, the volume, the spaces, the things that we're working in, how complex scenes are, trying to cast a ray on something, hit an object, and so on. And it all kind of comes down to, a lot of the challenges here are issues of complexity, how to figure out, like you mentioned, the ray cast, does it hit an object? How are we representing that object that needs to be hit? How do we figure that out? Right? That's tricky. And that's actually one of the challenges of things like ray tracing and path tracing and kind of rendering at that kind of ultimate level that we theoretically like to, and it gets used a lot in our Hollywood movies and everything, our actual ray tracing, is this idea of how do we figure out how the light hits an object? What does it hit? Right? Complex objects, it's tough. Why do we see so many early ray tracing examples using marbles and spheres and so on, right? Because it's easy to see if a ray hits a sphere and figure out where it hits it, right? So that's kind of one of the reasons that happens, and it's kind of clues you in on where some of the still complicated pieces of graphics are, right? This idea of model complexity. How do we represent these models? How do we figure out, do we hit them, and so on, right? So we'll get a little bit more into ray casting, ray tracing, ray tracing, path tracing, and I think I posted it in our general area, or if not, topics. Oh, even this is getting a little bit. Here it is, yes. I'll grab this, and I'll copy that link and put that over in our lecture blog. Right? Talking a little bit about these different issues and the differences between the rasterization approach we have now, ray tracing and path tracing. Right? So leave that there. We'll actually talk about that a little bit more next time. But along the terms of the complexity question, and how do we represent models? Right? So we're always faced with this idea of complexity of models and complexity of surfaces, and how do we represent things? So I wanted to kind of close out some of the stuff that was in the text that we used to use, and also is kind of an important topic-wise, and we talked about earlier on in the course, things that we do to simplify the representation potentially of complex objects, and how we can take advantage of that, how we can represent them, and how ultimately we can use the hardware and some of its capabilities to kind of present them. This doesn't solve the problems of hitting things, though, right? So it's you sort of get to a crossroad where you're saying, wow, I can make these really, really complicated looking things, but we're always faced with this, how do I click on them? How do I interact with them? How do they interact with one another? How do they collide? How does light collide with them? Right? So even if we're not trying to say, well, I want the player to walk on the surface, which is probably even a more, or might think of it as being the more complex interaction, we're still facing challenges of how do we interact with these surfaces? How do we interact with things and so on? So let's talk a little bit about some of these and wrap up we'll call this the Gordon and Clevenger text things, which I know we don't have that text, but I want to at least cover the topics via this. So I'm usually not used to doing this directly inside PowerPoint, but let's give it a try. Slideshow, here we go. All right, so the first thing I want to talk about, there's actually kind of a three-part. We'll see where we get. Right, these three go together, and these are definitely more conceptually they've been around for a while, but they're one of the newest features in OpenGL 4.0. And even OpenGL 4.0 isn't all that new, but it's one of those things that's not supported by every version. You start to run into issues once we hit kind of...
Hey, Professor?
Yes?
Are we supposed to see something on...
Oh, you're not seeing it?
No.
How about now? Do you see it now?
Still no?
You just see a blank screen?
You're not like streaming on Discord.
Oh, whoa, 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 sorry. I'm recording. Oh, gosh. Wow. All right. Could have warned me about that sooner. All right. Sorry about that. Oh, gosh. I thought for sure it was some kind of hardware problem on my computer. All right. Well, you missed out. Okay, I'm going to show you Octopath Traveler just real quick so you can see that in the background here. So anyway, that's Octopath Traveler here, where we see the our hero in the mid plane, or the mid region of the screen, is nice and crisp in focus, and then the background and foreground has these wonderful blurry effects, and so on. All right. So let's get back to that. All right. And since it wasn't up, so here we talked a little bit about that OpenGL, or that 3D picking. So here's a reference to that, in case you were wondering. So just quick recap. Wow. And, well, won't worry about that. And the reference to this page, Future of Gaming Rasterization versus, and so on. Wow. Okay, now, parametric surfaces. Everyone can see this one. Yes?
Yes.
Okay, all right. Okay, so a few new features of OpenGL, two major features, is this notion of tessellation shading and geometry shading. Right? The idea behind both of those are ways to handle, kind of introduce or parameterize complexity and give it to OpenGL, give it to the hardware to help us rebuild complex things, right? Mostly with regards, you can imagine you could do this, not just with regards to rendering, but perhaps, there's also compute shaders and other techniques you can do to help with, the collisions and all that kind of stuff. But for now, just thinking about, the complexity of surfaces. So, how do we, given a little bit of information, represent something that's more complex? That's kind of what we do all the time, really, in OpenGL in our typical modeling, right? We're only representing certain vertices and their position, and then we extrapolate or interpolate all the stuff in between, what's on the polygons, right? We're not representing models at a pixel or even voxel level, right? Is everyone passingly familiar when I say voxel, what I mean, right? A volumetric pixel. Imagine the complexity of a model if we said, okay, I'm representing every position that model occupies, internally and externally, or maybe it's just the hull, or maybe it's just the shape. And at every one of those locations, I have to have the information like the normal, effectively all of the PBR types of textures that you'd have, the ambient occlusion, the roughness, the metallicness, all of those sorts of things, right? You would have to have that information for every pixel there, right? That'd be the ultimate, or every voxel. That'd be the ultimate representation. If we could actually, get to that point, sort of like, imagine, having atoms. So we really need that representation. We could truly do everything, but it's always this kind of abstraction to say, well, all right, what's the minimum I need to describe the model in adequate fidelity and then present it to the viewer? So parametric surfaces, we should be a little bit familiar with a little bit. We remember our friend Pierre Bézier, and he's one of the people we should know about. Jump to mind, okay, Bézier curves. Okay, we know about him, right? Other people we remember, Sutherland, from way back when. You might want to look at early lectures. Remember what he did, where he was in terms of things. Folks like Blin, Fong, Garreau, those big names, you should know what they were involved in. But anyway, Bézier falls into that class. And we looked at them a little bit earlier on when we were talking about 2D in our rasterization. We did lines with Bresenham, and then we did curves, simple 2D curves with a simple Bezier spline approach. Now, you can, of course, like so many 2D things, extend that into 3 dimensions, right? So we can create a smooth, curved surface out of a grid. Pardon, this frame is a little bit weird, but out of a grid of regularly placed, or a much more sparse grid of control points, basically. Right, so we have a grid of control points, and then we have the math behind it. Right, so we can use our Bezier curves, in this case quadratic Bezier curves, to say, okay, the pixels in between, the space, the surface in between, how can we reconstitute that from these given control points? Right. So in the example we did early on, we had some simple examples of setting up control points, and then ultimately it is an interpolation of the positions in between, given those inputs, given the amount of influence of the control points. Right, so in this case, look, we have 3 control points, P0, P1, P2, and we have some parameter t between 0 and 1, the fraction of the distance between any of the control points. We generate the curve by collecting the points created by all the values of t between 0 and 1 if we want to have the curve along that spline, that Bezier curve. So we love our math, but ultimately, like I said, we can view this as sort of a elaborate case of interpolation, sort of weighted interpolation according to some control, right? We wind up, as we did in our homework example, using the cubic Bezier curve, a set of 4 control points, right? We should remember that way back when. Right. So the idea is that you can subdivide and interpolate, right? Ultimately, we wind up with a way to generate points between those control points along those parametric surfaces. Right? So here, in the end, we have a 3x3 quadratic Bezier control mesh and the corresponding surface. Right? So we have a very limited number of points, but a nice, smoothly changing, smoothly curving surface underneath. Some examples. Now here's a 4x4 control mesh and the corresponding surface. So you can imagine if you wanted to create a model that was very smooth, it'd be nice to apply this as well. And you may have seen things like subdivision surfaces. If you've worked in tools like Blender or even other applications where you say, okay, let me generate a hard mesh, and then you can apply a subdivision surface to that, or some sort of subdivision operation. Often that will be using kind of this sort of thing where it'll basically subdivide the hard surface and then apply a Bezier solution to get the curved areas on there. Right. So that's the main concept here, right? Using parametric methods to approximate or to kind of abstract these smooth surfaces, these curved surfaces. So that's sort of part 1 of the question. The next part is, of course, well, how does that map to what we would want to do in OpenGL. What tools do we now have at our disposal? What is this about this tessellation shader set that I mentioned? What makes this applicable? What makes this useful? Okay. So we have tessellation. Now, tessellation, the tessellation shaders, and there's two types of tessellation shaders to talk about in just a second, they occupy a special part in our OpenGL programmable pipeline. They sit in between the vertex shader, or like right after the vertex shader, basically, and way before we get to the rasterization fragment shader, the stuff that we're used to. Because what is it, their goal, what's their purpose, is basically to take a set of points, right, to take some geometry and allow us to subdivide that geometry down to a point where we can have, say, that control grid, some of what we had just showed in the 4x4, 3x3 examples there of using that to create a surface. Right? So we can use our tessellation shaders to, on the fly, take our geometry and automatically subdivide it according to certain parameters. Now, we'll talk a little bit later about the next phase, the next new phase, which are geometry shaders, which help us sort of weed out or enhance or further refine the type of geometry that we're creating, or even simplify it for other purposes as well. So here we are now basically in this primitive triangle processing phase now that we're newly encountering. So the tessellation stage is a stage that we generate a grid of vertices. And we have now obviously support for hardware tessellation through these specific pipeline stages. We have the tessellation control shader, which is programmable, right? Shaders are the programmable piece. Then there's the tessellator piece, which uses the setup that we provide in the control shader to create our grid. And then we have our tessellation evaluation shader, which allows us to basically start moving those control points around, to process those control points and do what we want to do with them. Right? So the TCS and TES, the tessellation control shader and the evaluation shader are the programmable bits. And OpenGL has the hardware support handle the actual tessellation. Right? We create these shaders, we compile and link them just like other shaders, but of course we have some special enumerations for them, so we can tell OpenGL what type of shaders these are. And we have some more new syntax to say, well, all right, well, if we're doing tessellation, there's going to be some new attributes that come from the vertex shader arriving to the tessellation control shader. And if you think about what we just discussed, you're always using multiple points to generate your new geometry. So a single vertex is not enough to create some sort of parametric surface. So at this point, our vertex attributes, we wind up getting multiple vertices passed to the tessellation control shader so that it can do what it needs to do. So in the example case, or theoretical case here, the idea is to display a grid produced by the tessellation stage. Right? First thing you'd want to do. So your application, things would be fairly normal. Your vertex shader actually winds up being fairly normal as well. You can just pass that in. Imagine, we could, in our case here, maybe just take a quad set of, normal, simple geometry. And the important parts are down at 3 and 4. What the tessellation control shader, you tell it the grid for the tessellator to build, and then you evaluate your new vertices, you have to basically run sort of your MVP, well, not sort of, but yes, your MVP transformations and so on, because now we have new vertices to process. So we have to apply our MVP matrix to the vertices in the grid. And then the fragment shader's job really doesn't change much. It doesn't realize, are we talking about real fragment positions or synthesized ones? Right. Now, the big thing to notice here, I'll just draw your attention to this part. GL draw arrays. We have a new primitive here, GL patches. Right. So we are not drawing triangles here, not drawing lines. We are actually drawing patches, and that's the piece that tells it, okay, how many vertices belong to a patch, and how does it get passed along? Right. Here's some really simple examples of what a tessellation control shader and evaluation shader would actually do. The main job of the tessellation control shader is to say what level of detail, how many subdivisions am I going to try to do to this patch. You'll see it is outputting vertices here. And it has these main things that it has to deal with: the outer and inner subdivisions. So it has, this one is using subdivisions, 6 subdivisions along the outer edge of the patch and 12 subdivisions along the inner edge of the patch. Now, what that means will become hopefully evident in a second. Right. The evaluation shader in this one is pretty simple, right? It's just taking our new tessellated geometry coordinates and transforming them according to our normal kind of typical thing we do here. Right. So here's the idea. Here's the result. So we start off with a patch that has corners, and if you look carefully now, nobody gets hurt. We have 1, 2, 3, 4, 5, 6 subdivisions along the front, left, back, and right edges, depending on what your orientation. I guess I should have said right, back, and left. And then inside, so after that first subdivision, this is the inner subdivision, it has 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh wait, no, sorry. This one here. These are the 12 across here. Right, we have to go in one because these. That's where the half. That's why we cut in half. You can get even fancier in here, and it will do. It doesn't have to necessarily be a 2-to-1 orientation, but this is sort of the basic version. The nice thing here is now, well, okay, now we've got more vertices to work with. So if we were to do something like a height mapping, where we wanted to now take a flat surface and use some sort of height map to start pushing pixels up and down on that surface, we could do that. Or if we wanted to move things along that surface according to a parameterization, we want to create a parametric surface out of this, we have lots of vertices we can work with now. Right. So here's our conceptualization here, outer level and then inner level of our subdivision. All right. So here's what happened. We went from our vertex shader that had our control points, our patch. We then handed that to the control shader, which the tessellator then used to create that grid. And now in our tessellation evaluation shader, we can modify those vertices, make them do whatever we want, put them where we want them to be. And then the fragment shader will just do its thing. Right. So we have, to go along with it, some built-in variables. In the tessellation control shader, we have the incoming control points, basically the definition of the corner of the patches. The output sending the control points out, just in case we wanted to modify them, change them, things like that. We have an invocation ID, similar to our built-ins like our index or our instance or ways of kind of knowing where we are in terms of processing our model. This is a counter indicating the invocation of the TCS is currently executing. So if you wanted to do something even more complex, divide subdivided surfaces and so on, there are ways to further break down surfaces and so on. And then ultimately, the tessellation evaluation shader has to bring in the value, the new position, the newly created position, and give it an output position. Right? So I'll leave this as example code if you want to dive in. Right. So that's the quick result. Without getting into too much detail here, I guess I should point out this part though. We see in our tessellation evaluation shader here, we are figuring out the locations of our fragments ultimately, or they according to our calculation of the Bezier curve here, right? So that's where applying everything we just talked about a little bit in the parametric surfaces. Right? So that's what happened there, and we wind up with that output position that is now along the spline or along the curve, and we have then transformed that according to our MVP matrix. We can also then interpolate our texture coordinates, mix them, which winds up giving us this even smoother version of our, or appearing, what appears to be even smoother version of our texture and so on. Right? So one big application, potential application of this, is in terrain generation, as you can imagine, right? You want to set a peak. Here's a mountain, here's a valley, here's, it's ripe for this sort of thing, right? So the strategy typically for these doing a tessellated terrain, use the tessellator to build a grid with some large number of vertices, and then have some sort of height map that you can then use, apply to that in the tessellation evaluation shader, computing approximate texture coordinates, and so on. And the example and the result, pretty good, right? We can wind up pushing things around, right? But ultimately, the problem is still, in certain circumstances, is going to be, well, do you have enough detail? Right? In the background, maybe you can get away with that. In the foreground, well, it becomes even more of a problem because it's potentially, changing, more or less detail in the front. Imagine having those, only those 12 or 6 subdivisions in the front. So there's this notion I mentioned about, how to create, use some sort of instantiation or create greater resolution in your grids so that your tessellation can be perhaps, almost like a MIP mapping sort of approach, where something is closer in the scene, you will be able to add more detail to the surface to match potentially the surface of a complex height map and so on. Right? So you can use the tessellator and instancing to build several grids of generated vertices and wind up with different versions, things that are closer. Now here, obviously we have even more detail. We do wind up in the simple approach, though, with problems like, since our height map, light is high, dark is low, it doesn't look particularly realistic. Why? Because the height map and the color map kind of potentially fight one another. We didn't actually have a 3D scan of the moon here, so we're kind of simulating that height map according to the color. So take it one step further, incorporate both height and normal maps into the shader, or to the set of shaders, right? So now the tessellation evaluation shader needs to do things that our vertex shader used to be entirely responsible for. Things like the lighting computations. Normally they would have been done in the vertex shader. Now they have to be potentially done in the evaluation shader. So you'll see that often your tessellation evaluation shader will look a lot like your original vertex shader did with regards to the kind of calculations it would perform for lighting and for texturing. Right. So now, in our moon example here, if we had a height map and a normal map, use all the techniques together, we can wind up with a fairly compelling surface now. Now, going one step further to really embrace the idea of something far more MIP mapping-ish rather than just using instancing, we can vary the number of vertices based on the size of the area being rendered. Right? So we can control level of detail. Now we want to have not something broke down into multiple instances of varying detail, but having it done kind of more automatically. Right? So based on a certain size, we're going to dynamically vary the number of vertices based on the size of the area, the size of the patch. So not just the size of the patch, but ultimately the size of the patch with regards to what the camera sees, so kind of based on that distance. We have to kind of use these things together. So we're using tessellation, varying the tessellation levels based on distance from the camera. So, multi-step process here, which first involves, now we have the patch, we have to figure out the corner of the patches, where do they lie? So calculate screen locations of the 4 patch corners by translating them according to the MVP matrix, right? Calculate the length of the sides of the square determined by the control points. The side lengths can differ because of perspective. Remember, we're looking at things that have been varied. We want that perspective because we want things closer to have more area. Things that are further in the background, we want them to have smaller area, right? So we're actually taking advantage of the perspective there to figure out these lengths, these sizes. So after applying that, scale the length values depending on precision needed for the tessellation levels based on the detail in the height map. That's determined by, ultimately how much detail you have in the height map. Add 1 to the scaled length values to avoid the possibility of specifying a tessellation level of 0, which would be bad because that would just basically collapse it. Set the tessellation levels to the corresponding calculated width and height values. So now our tessellation control shader is doing a bit more work. Right? It's not just setting up the same width and height for our whole grid. It says, okay, for this particular patch, it's closer to the camera, so I can figure out dynamically how detailed should that particular patch be. So now, one more step, combining texture mapping, height mapping, instance tessellation, and level of detail. All right, so we wind up with a grid that is generated from multiple instances of a simple grid, and then applying different levels of detail to each of those instances, we wind up with this. This is more a housekeeping issue. OpenGL Tessellator provides support for reducing popping artifacts by altering the configuration of the tessellated grid. So basically allowing for equal or fractional even spacing. So it's basically saying, all right, if two grids are next to one another, make sure that they don't vary excessively according to how they're tessellated, right? So you don't wind up with a high detail next to a low detail tessellation, right? Somehow they have to have something smoother, like this fractional even spacing, potentially. All right, so that's the whirlwind tour of the job or jobs of the tessellation shaders, right? Basically giving us the platform to put in place parametric surfaces and to, even if we're not using parametric surfaces, ways to generate complex geometry, or at least planes that have positions, have enough vertices to take advantage of things like height mapping and other types of geometry manipulations that you might want to do in the shaders. Right? You can even just entirely dynamically generate random noisy surfaces or smooth terrains or whatever you want with these. All right. Does everyone get that conceptually now, right? Why these things are important, right? If you won't worry so much about the math, but the main ideas now is we're taking grids, we're using our friends, our Bezier curves to say, okay, now by knowing a certain small set of points, we can map, we can create these smooth, basically interpolated curves between fixed, a small number of control points. We just need the hardware to help us out to actually do all that in a effective, efficient manner. So let's finish off the trifecta here. And the last one. Now, geometry shaders, it sort of, you can, how did I get this backwards? It should be 13. We didn't talk about them in chapter 2. The idea with geometry shaders, we certainly could have covered them before tessellation shaders, because you don't have to be doing tessellation to want to take advantage of geometry shaders. But they potentially become, even more useful in those cases because we are generating extra geometry. But for now, let's some of these examples we're basically going to say, well, okay, let's look at them in the abstract. So they occur after the tessellation shaders in terms of the pipeline. Of course, we don't have to be doing tessellation to use them, though. So geometry shaders, it is another class of these kind of primitive shaders as opposed to vertex or fragment shaders. It's a stage that enables manipulation of a primitive. Now we can go back, we can manipulate, say, triangle primitives. Right? And this is nice because now, instead of just getting a single vertex, because this is a geometry shader, this is a geometry primitive, we'll have access potentially to all of the vertices that belong to a certain primitive. So in the case of triangles, you're going to have access to all three vertices of the triangles at once. So you can do kind of cool things to them. You can say, well, throw out that triangle, or do something to it. So geometry shaders allow you to do things like just pass things through. So you have a triangle, just passes through, doesn't do anything because it meets some criteria, perhaps. Or you can do things like change the triangle, manipulate it somehow, modify all of the vertices if you like. You could even emit, not omit, but emit additional triangles, right? Create more primitives based on that, right? So you could do your own types of subdivision, right? Your own tessellation, basically, if you wanted to do something sort of based on some kind of manipulation there. We'll do things that are kind of like that. So output a different type of primitive, such as a line, or delete the triangle, no output at all. Right? The process of creating them winds up looking very similar. From the CPU side, we just create a shader. We now have yet another enumeration, a geometry shader. Just like the tessellation, we wind up being passed in the vertex attributes in arrays, because we're going to have multiple vertices passed at a time, potentially. And ultimately, the vertex attributes output by the geometry shader are scalars, right? The position and so on. So the exciting parts really are this notion of emitting new vertices or emitting new primitives. So you emit a vertex, you specify that a vertex is to be output. You generate a new vertex. Oh, sorry, end primitive, not emitting a primitive. End primitive indicates the completion of building a particular primitive. Right? So if you want to build a new triangle, right, you have to emit 3 vertices. So you emit those 3 vertices, and then you end the primitive. Sorry. We have another built-in parameter, a built-in variable primitive ID in, holding an integer ID of the current primitive. So as you create them, they're going to start at 0 and work their way up from there. Right. So this first example is one of just creating, altering the geometry. Right. So it's sort of like in most cases, we were able to modify a single vertex, but now we're going to be able to say, okay, given all 3, given that triangle, let's move the triangle, right? So here we're going through and we're looking at each of these and emitting a vertex according to its new position. Right. So move vertices outward along the surface normal. So this is nice. We can actually not just move individual things. We can figure out, okay, the surface normal of a triangle, of an actual polygon triangle, we're going to move them out, sort of explode our model, or inflate our model here. Right. We're not allowed to do it to every type of primitive. We're a bit limited. We can't do quads. We can do points, lines, strips of lines, adjacent lines, triangles, or adjacent triangles. Right. And they can be points, line strips, or triangle strips. Right. So we can also do things like, here we're moving the vertices outward along the surface normal averaged by the entire triangle. So it's a little bit odd. So the idea is that in the end, this triangle is moved up to here, right? We figure out the normals in here. We don't want to stretch. We don't want to inflate, right? This is the opposite of inflating. Not the opposite. That'd be shrinking. It's different than inflating, where everything is increasing in size and everything still meets. In here is more the exploding versus inflating, where we just figure out, okay, move each one of those triangles without changing its size, right, which does this. Right? So we move them all out. They haven't increased in size, so now this is more the exploded view. Right? We end up seeing the inside here, except just like with our clipping, it doesn't realize that suddenly, because of that operation, now you can see inside. So we don't see the back of the torus. We only see what would have been the front of the torus to begin with, because it's only passing us those things. We've culled the back faces, so we didn't explode the back faces in here, right? So we need to be aware of that sort of thing, right? So the exploded version, if you want to get it to see the back faces, now we've got to mess with our culling. Basically, are drawing the back faces, drawing the front faces, or actually drawing the front faces, then the back faces. All right, so now you can't see it too well on the projection here, but on the other screen, hopefully you can kind of see that. That yes, we wind up with the back part. So culling becomes really important for doing things like, we've seen it in transparency, we've seen it now in exploding things, when we start clipping geometry and something can kind of see inside, right? So don't underestimate the need to understand how your culling is working, right? Your back face culling, front face culling. We also used it, we talked about it when we were doing shadows, right? Because in certain circumstances it makes sense to figure out where the back surfaces are, right? Because that helps take care of certain artifacts by using the back faces and seeing if are they shading versus the front faces shading, so you don't end up with that shadow acne or that kind of where it's saying, okay, this surface is in view but shaded by itself, right? So that's why it was nice to have that, play around with the back faces and culling. So just remember that. And next up, deleting primitives, right? So now we've changed them, we've modified them, we've moved them around, exploded and inflated, and now we're going to say, all right, given a certain index, the primitive ID, so every other triangle, perhaps, right? We're using a mod here. Oh no, every third, I guess, right? So we're modding our primitive ID by 3, so it's going to go 0, 1, 2, 0, 1, 2, 0, 1, 2, and say, okay, if it's not equal to 0, oh, well, in this case, we're modding a bunch of them. We're clipping a bunch of triangles out, right? Everybody know what I mean by mod, right? The mod is the division without the remainder, right? So we divide by 3, we get the remainder. So if it's not equal to 0, it means 2 out of 3, basically. On 1 and 2, remainder of 1 and 2, it will process this. Remainder of 0, it will not. Right. So here's the result of that. A fun one. Creates a real interesting pattern. Wind up seeing the inside of the torus again. So, well, you can go through the whole result. We won't look at that code again, but now, all right, let's do it similarly, same code, but include the back faces. Now, what if we want to add more geometry? We basically want to convert triangles into pyramids. This is an interesting one because we're going to basically say the original triangle is going to be the base of our pyramid, and we're going to use the average of the normals to figure out what the apex of the pyramid should be. Right, that's what's going on in the first part. Right, we average the normals, we get that point, which is the top of the pyramid there. Some code that basically does, we're taking the average of these, creating our new positions. We are making new triangles. What does make new triangle look like? Make new triangles really where the magic is, right? We figure out a normal, we figure out the positions. So for each vertex, we have a position and a normal, and we emit the vertex, we end the primitive, right? Because just like our other types of geometry, not only do we need things like the vertex positions, but potentially we need our vertex normals. If we were doing lighting, if we were doing anything more advanced, we'd need to be generating all the output values for that vertex just like we would have as well. So we're here generating a new position and normal for each of them. Here's our new faceted torus made of tiny little pyramids. All right, another fun example. This is kind of the fur example. Right? So say for every polygon, for every triangle, we want to put a blade of grass or a fur, a piece of line, just a line. Could be something even more complicated. Here we're doing just a real simple one. So we're going to replace the triangle with a line. We're going to take the average the vertices to get the center of the triangle, average the normals to get that new point, which would have been our top of our pyramid, and we wind up with this new line primitive, right? Just two vertices, right? So the geometry shader, we have the original triangle vertices, all three of them here. The original offsets now according to our normal. So the normal plus the position. Then we calculate the new points, basically collapsing them, taking the average of them. And we wind up with a bottom. We emit that vertex. And a top, and we emit that vertex, and we end the primitive. Right. So we wind up with sort of the kind of like a magnetic field or something, kind of a cool effect. The furry torus, geometry shader for changing primitive type from triangle to a line. Now, you could, of course, do things like include the original. If you wanted to be fancy, you could be having things like changing the color, right? Here, we're just talking about simple shading that is just based on, we're just using the coordinates and normals. We're not doing things like texturing it or coloring it or, doing fancy lighting and so on. But all of those typical other things would apply as well. All right. So, key topics about the tessellation shaders are ways to create these sort of subdivision surfaces, create normally subdivided or parametrically subdivided new geometry patches automatically in the shader using the tessellation control shader, and then either just outputting those normal grids or taking advantage of things like parametric surfaces and so on in our tessellation evaluation shader. And then in our geometry shader, doing things like changing our primitives, adding new primitives, moving vertices as a group of primitives, or sorry, the other way around, moving primitives as a group of vertices as opposed to manipulating single vertex at a time, which is kind of tough to figure out, am I in a triangle or not? Can't really do that in a typical vertex shader, right? So this was a good whirlwind worth of stuff. Now, if your hardware supports it and you want to take advantage of this in your project, I will post this with this sample code in there. This sort of stuff isn't part of our typical Learn OpenGL, right? There isn't really there isn't the geometry shaders and tessellation shaders in our Learn OpenGL. So you should know the concepts. If I ask you, what's the purpose of the tessellation shader? No, you use, automatic subdivision of patches. That's a good one-line beat, something like that. What's the purpose of geometry shaders? Introducing, manipulating vertices on a primitive level, so on. If you want to take advantage of them in your projects, good. So you can expect some kind of questions, conceptual questions of it, like on the test, but you don't have to necessarily use them in your projects. Yes?
Are tessellation shaders any more expensive than standard vertex
Now you have to remember you're going to wind up with lots more geometry, and lots more stuff for the potentially the fragment shader and stuff and to do. So the result of them can wind up being, right? Anytime you're adding more geometry, you're giving your shaders more work to do. So, want to be careful. Right? Most of the time, it's to save work and certainly you can imagine shifting lots of stuff back and forth between the CPU and the GPU if you were like trying to actually create these very complex models that had smooth surfaces and so on. You'd spend all your time just transferring data and trying to manipulate that on the GPU or the CPU. That would be bad. But they're generally, as it's also certainly up to how it's implemented. I don't think you necessarily have the same number. I forget dedicated compute or dedicated GPU units of what type of shaders are supported and so on. So. Will it handle, well, if you have 1 million runs through a tessellation control shader, that's implying you're going to wind up with a lot more than 1 million running through ultimately your tessellation emission shader, tessellation evaluation shader, and so on and so on. So you probably don't have, you're going to always be processing, almost always be processing more vertices than you would patches, so the number of calls to those tessellation control shaders would typically be a lot lower than the number of calls you'd have to a vertex shader. So even if they are a little bit more expensive, they are also a lot less common. They should be theoretically a lot less common. Okay, so as far as the quiz goes, so I was kind of in that quiz land for a moment there about what to kind of expect in terms of this. I think, let's see. No, that's not an LMS. Sorry, I thought that was my LMS tab. So the syllabus has us down for, I think it's the second. No. Correct my grammar here. Monday, August 2nd. So things are, we're getting to that stage now where things are just, steamrolling, or that rock rolling down the hill is certainly, or snowballing. I don't know what the right term is. But I would like to push the exam actually to the 5th. So not next Monday, right? So August 5th. And what I'm going to do is there is going to be a homework. The purpose of that homework will largely be a review of some of the stuff that we'll have on there on the exam, the quiz. So I will give you a homework on this Thursday, and we'll have the exam next Thursday, right? So that will be sort of the schedule of things. One thing I want to draw your attention to, I posted this, is, and I can't emphasize this enough, at the Learn OpenGL site, there is a review section for getting started. Oh, my connection is a little slow, laggy this morning. All right, with a really good glossary of things. All our greatest hits: vertex buffer objects, array objects, element buffer objects, uniforms, textures, MIP maps, and so on and so on. Right? So this is a really good list to pay a lot of attention to. It's not going to have everything necessarily on it. IMGUI isn't on it. I expect you to all know what IMGUI is. Also, generally, what IMGUI stands for. What's the difference between, immediate mode and retain mode, which is one of the reasons why IM GUI is called IM GUI. So you should know some of the concepts on there and some of the concepts that aren't on there, right? But the general things in here. And under lighting, there's also a review section. Notice it has a lot of our friends on there: Fong shading, Garot shading. Right, so some of the basic things. The Fong lighting model, ambient lighting. Certainly if I asked what does ADS, what are the different parts, what do they stand for, right? But these two things are really, really good for review. Another good section for review, and I posted this, it's just a good resource in general. Oh, wow, internet. Is everyone streaming movies right now or something? No, not OGL Dev. OpenGL tutorial. The OpenGL tutorial cheat sheet for math is pretty good, right? So you should be at least familiar with those concepts on there. I've mentioned it before, so I'll post a link to it. The one big topic that's not on there, right? Obviously, we should be familiar with vectors, homogeneous coordinates, cross product, dot product, matrix multiplication, and so on. It leaves out our friend quaternions. You can't escape here without at least having some of the basics of quaternions. So, love mentioning this. We talked a little bit, I think last time. I'd love to just sort of review quaternions being sort of the special case of an axis angle representation, right? Axis angle, ultimately, it's kind of it's a chicken and egg, right? So quaternions are largely invented as a way of doing three-dimensional matrix multiplication things. It's more abstract than what we're using them for in computer graphics. So sometimes it's easier to think of them as in terms of a topic that is related to us, like our axis angle rotation. But some of the key differences are in that representation. So just remember, a quaternion is not directly an axis angle representation, but it is based on that and related to that, our use of them at least. And there's a very good video, which I'd like to recommend for you in terms of quaternions. This visualizing quaternions with stereographic projection. It's a good one. It is, let's see, lengthwise, it's not incredibly, that's a half an hour. But it's a half an hour reasonably well spent. And some of the nice things about it particularly is it will deal with a little bit of the history, and it starts off from goes through one-dimensional, two-dimensional, and three-dimensional. That's interesting. That is not what's on my screen. There we go. So it goes through a combination of, starts at one-dimensional, then two-dimensional, and three-dimensional math, and specifically multiplication. And it does a good job, particularly because of the way the things are sort of visualized in here. They're kind of, everything is related to really showing graphically how multiplication is such a natural way of representing or thinking about our rotations there, how multiplication and rotations are related. So I'd like to leave you with this video that you should watch. Again, if anything, with regards to quaternions and what you should be prepared to, if you need to kind of whip out any kind of cash from your quaternion wallet, we'll just say, it's mostly going to be this. I'm going to ask this one thing for you to have at the ready. Because thinking in terms of axis angle and thinking how we represent quaternions. Oh, I've lost the link. Oh no, here it is. This is one of the best single liners I've seen. And it's nice because it also includes basically the formula here, right? So quaternion represents a rotation by a 4D vector. That's pretty heady stuff. Requires more math and is less intuitive, but is a much more powerful representation of that rotation. They are easily interpolated, and that's one of the main reasons, right? Because the problem with applying multiple rotations in Euler space, however you want to pronounce it, we have those issues like that gimbal lock. That's something else we should remember, gimbal lock, right? Collapsing multiple axes basically down, so we wind up with rotations we can't do because of aligned axes. Right? So quaternions are easily interpolated, and it is easy to apply them to a 3D point. And here it is. Those formulas for the multiplication are easy to find on the web. Given a rotation of a radians around a normalized axis n, right? So we have our rotation, our axis, our angle, and our axis. The quaternion 4D vector will be, right? You have to remember the exciting or even confusing, or there's lots of questions about why do we use half angles, and there's some good discussion of that in another presentation. But ultimately, we don't have just the angle. The W value, the real value is the cosine of half, the cosine of half the angle. And then each of what we would think of as representing that axis is actually the axis multiplied by the sine of the half angle. Right? So that's how we go from kind of a typical axis angle to the quaternion representation of that, so that the multiplication that we do works correctly. And there's a bunch of reasons for that I'll leave to that video to explain. Right? Basically has to do with, as you apply the rotations, do you wind up with pure quaternions as a result, right? You can get in situations like if you are using these representations and you use the real angle, then you wind up with without you don't here. Let's see here we have a one-liner. Where's my one-liner? I will find that for you again and post that in the blog. All right. So I thought this was the page that had it. Here it is. The quaternion can do such a generalization, identifying a 3D vector with a pure imaginary quaternion, right? And using a pure imaginary versor U to identify the axis of rotation. When we calculate the product, if we're only using the angle and not the half angle, the result is not necessarily a pure imaginary quaternion. so it is not a vector. So this is getting into this kind of mathematical specificity that certainly goes beyond some of the scope here. So, but the reason you can find a pure imaginary quaternion only if you perform the multiplication. We have to multiply by it and the conjugate. That really represents a rotation about the axis, but the angle of rotation is now doubled, so that's why you have to take the half. Right? So take my word for it that there is a good reason going back to the more theoretical and strict ideas of working with quaternions, why we're using half angles. There are ways kind of around that, but it usually winds up being some sort of messy special case. But you just need to kind of know that it's those half angles, that you use cosine of the half angle for the rotation, and then you multiply each of the axis components by the sine of the half angle, right, to keep it as a pure imaginary quaternion. Right. So the result is still a vector that complies with that. And that is a big chunk of wow, right? We'll leave that, and the big extra takeaway is to watch the quaternion video, visualizing quaternions. All right. One other last bit, a few things. I think I've posted this in the blog as well. Go and post the links here. Key things: future of gaming, rasterization versus ray tracing versus path tracing. We'll talk a little bit more, through the quick version, getting more into ray tracing and path tracing again next time as well, because I do want to have some basic questions on that in that exam. So one of the differences might be, well, what really is that difference between rasterization, ray tracing, and path tracing? So this link is a good step through. Rasterization we should all be familiar with, right? This is what we're doing in our day-to-day OpenGL. Right. And then ray tracing and path tracing. Read through these sections at least, and we'll discuss a little bit more next time. The subtleties of each of them. And there's the differences between the two of them, and there's also going to be a link if you want to go even in more depth to that ray tracing in a weekend, which really goes through the whole process. And one of the key things here to kind of come full circle, what we started talking about in the beginning. Why? Method to my madness. One of the key things in ray tracing is ultimately, you'll see in most of these ray tracing examples, the question that I had for the longest time is, well, how do you represent things in there? How in your ray tracing, are we using models? Are we using, we talked about coordinates and vertices, and how do we, what's the representation in here? And I mentioned earlier on that quite often you see these ray tracers using marbles. Right? In the end, they look really, really pretty. And very compelling, very realistic. But they rely on sort of a simplified, here, again, it's easy to figure out light colliding with a sphere, or a ray colliding with a sphere, as opposed to something colliding with a complex object. Right? So in talking about next generation things that are going to become important to hardware, like in RTX and so on, or figuring out the bouncing of those rays, how they collide with one another, how those pieces are handled. And that's what we're starting to see in the hardware now, the hardware engines that are supporting that RTX, right? There are these hybrid models. We're still going to use the models that we're used to, but now our hardware is going to allow us to do things like calculate all those bounces, right? Calculate, are we hitting an object? Right? So much of what you see in here ultimately is like saying, you know, you add everything to your scene, and then you're saying, what does it hit? What does it hit? What does it hit? Right? So think about that collision and the bounce. Right? That's really that key piece of things as we talk about ray tracing, path tracing, and so on. Right? So as you're comparing the other article, which is just the, that same one, yeah. As you're going through this article, slow internet, where it talks about the importance of different types of reflections and paths and rays and so on. And kind of compare that to if you need a concrete example, you can go back to your ray tracing in a weekend and look at that. But this fairly concise article will be enough to, if any exam questions come from it, they'll probably be coming from in there. And we'll talk more about that next week as well. Or not next week, on Thursday. Okay. That's, any questions, any more? Hopefully you're making progress on your projects, all right? Everything along there. I haven't gotten lots of questions and so on, so I assume everybody feels that they've got enough to go in the direction they need to. Do feel free to add other things or try other things or talk about how you could have added things or what things kept you from or why and so on. An important part of any dissertation is also what could have been done, what could be done in the future, right? Every dissertation always has a future work, you know. I know in my thesis, my doctoral dissertation is lots of future work. You know, it's easy to say that. Whether you do any of that future work, that's up to you. And maybe you do, maybe you don't. But think of that as we're talking about some of these techniques. How would you incorporate them in there as well? All right. On that note, hope
Hey,
you're...
Professor?
Yes?
Is there a requirement for the specific topics that we have to include on the project?
No.
So it's just show our knowledge of OpenGL?
Yes. And you know, and to what it is that you're proposing, that it is an interesting application. It can go beyond OpenGL. It could go into, you know, other applications of some of these graphic techniques. You know, if you are doing something that's not specifically implemented in OpenGL, check with me. You know, if you wanted to do something that's you know in another engine or in some other specific tool, but it is similar in complexity. You know, if you wanted to design a plugin, here's some really good examples. For example, if you wanted to, the asset store in Unity, they've had a great sale going on, and I've been looking at a bunch of different things in there. Some amazing tools, such as, you know, terrain generation, different types of renderers, different types of shaders, different types of things that are implemented. It's going to be the same concepts, but you know, some of the, you know, you may find it more or less intuitive, and the final project should be, you know, creative and conceptual. You know, have some sort of area that is, you know, you feel you're applying your own twist on things. But if you want to apply things in designing a tool or implementing something specific according to an algorithm by hand, even, that's okay. So it's pretty open-ended even with regards to OpenGL. I mean, if someone wanted to really dive into Vulkan, that's certainly an advanced topic. Probably should have already been on that path already. I wouldn't recommend that, jumping in at the last minute. That's really more of an advanced topic. So there's room. You know, if I've agreed to it in the proposal, then I've agreed to the proposal, so we're good. Okay? Sorry, I know that's a little bit of a fuzzy answer, but the final project is designed to be kind of a bit fuzzy. It's showing good development practices, but also focusing a little bit more on the conceptual and creative side of applying things as opposed to do this specific implementation of this specific detail or something like that.
Gotcha.
Okay.
Also, is the project, or how do we know that you have agreed to our project proposal?
Did you get a grade for it? Did you put it?
Let me check that.
In LMS, if you got points in LMS, that means yes. There were a few people I had some questions for that didn't respond, so basically everything sounded pretty good. And if you have any further questions on it, let me know.
Sure.
Right. Yeah, I just, as part of the sale, I got a terrain generator, a water/road generator, and what was the other one? A vegetation generator, right? A friend of mine years ago created one of the first big used in movies. I forget, it was a Star Trek or something like that, where they use the plant, kind of fractal-based plant generation. It's a really kind of cool thing. A bunch of SIGGRAPH papers came out of that. So if you want to potentially do that, normally that's sort of an advanced computer graphics to get into sort of that level of creation, but somewhere in between there and where we are right now, if you want to get into doing shading and geometry manipulation inside of Unity or Unreal, cool. Want to write a plugin for Blender? Cool. No one proposed that, but maybe next semester. Or if an independent study project, you want to do something based on this going into next semester, or that's cool too. All right. On that note, there's nothing else? Oh, there is. Yeah. How much could it be? It's kind of, I'll have to decide that in terms of, I don't want to give something as, my first response would be too, sort of, it depends, and I have to go back and consult my original wording on what I said on that one, whether it was to take how much of it could entirely take off, or how much is it an additive thing. I'll have to get back to you and post that. Okay. But thanks for reminding me.
Also about the essay, you said it was something like around 3 pages.
Yeah.
Is that like, do you include like images as well?
That, as long as you don't get carried away with that, 1 image per page, that's no more than 1/3 of the page. So we'll say 2 pages of text and 1 page worth of images, give or take. So yeah, it's too, in a graphics class it's easier. Oh, look at all these pictures. 1 paragraph. No, it's kidding. Okay. See everyone on Thursday, and have a good week. It's not so much a matter of staying cool. I think it's a matter of staying dry now. It's very humid now. That's the problem.